Hello guys, we would like to extend the root locus basics ahead. We will take third example to understand the basics by analytical mean. We will not analytical means we are not actually following the root locus procedure, and just by getting the number of points for constructing root locus, we will try to get the root locus plot. So in example number 3, we have 3 open loop poles. With this open loop transfer function having 3 poles, s is equals to 0, s is equals to -1 and s is equals to -3. These are the original locations of the open loop poles. There are no zeros of course, and k is the static parameter which we are going to vary. So with the characteristic equation, and after substituting this, h of s is not given means it is unity, and therefore we have the simplified characteristic equation. It is this polynomial is having the highest order 3, therefore there are 3 number of roots. By this procedure, let's have this sample points for constructing of root locus. With k, we as identified in the open loop transfer function, we have s1, s2 and s3. With k is equals to 0, when you substitute it, so we will have the locations at s is equals to 0, s is equals to -1, s is equals to -3. Likewise, with varying k, we have the multiple points for multiple points with respect to the k values. As the k increases, say k is 0.631, intentionally this value is taken. The reason is that beyond this value the root locus breaks. Okay, so there is an imaginary part in s1 and s2. s3 root still it remains on the real axis. It approaches towards the negative side. Here it is -3.55 for 12, for 40, and likewise if we assume maximum value of k, say 1000, 2000, you take any sample and based on that you will get the specific values of s1, s2 and s3. If we try to put those points in the s-plane, we will have the construction of root locus in this way. The first root values, it begins with this, the first root s1. Initially it is at origin and it is shown by this thick line. It approaches in this way. At some instant, at one value of k, it breaks and it comes out in the real half. In the same way, the s2 plot, it begins with s is equals to -1. Till this point, it remains on real axis and the locus breaks. The s2 locus, it travels in this way, and at the same value of k, that is k is equals to 12, both the roots s1 and s2, they comes out and they are now beyond the k is equals to 12 value. They appears in the right half, making system as unstable. For the third branch of root locus, initially it is at s is equals to -4, and this locus travels in this way. As k increases, it proceeds further and it moves away from the center, but remains on the real axis. So let us summarize the root locus. We have 3 number of poles, no zeros, and the number of root locus branches are 3. Okay, the first branch in this way, second branch like this, and the third branch on the real axis. This is about as domain, as it is observed that the value of k when till k is equals to 12 or less than 12, all the roots lie in the left hand side, so system is stable. Once the k crosses the value 12, the roots have positive real part, making system as unstable. So this is the relative stability. With the value of k, we can assess the stability. For a certain range of k, system remains as stable, and after that it becomes unstable. With these three examples, we will summarize our observations. The features of root locus are like this. The root locus starts from the open loop poles, as we have observed in all three examples. The root locus starts with open loop poles and terminates at either open loop zeros if they are available or at infinity. The number of separate branches of the root locus either equals to the number of poles or the number of zeros, whichever is greater, but normally the number of poles are more. A section of root locus lie on the real axis if the total number of open loop poles and zeros to the right of the section is odd. The root locus is symmetrical. In third example, we have seen symmetry. Even in second example, it was symmetrical. The root locus is symmetrical with respect to the real axis. This is again very important. At one point on the root locus between two open loop poles, the root locus breaks away. The higher value of k, the root locus can be approximated by asymptote lines, and these asymptote lines intersects at a point on the real axis. The asymptotic lines makes an angle with real axis at a point of intersection. If the root locus intersects the imaginary axis, then the point of intersection are conjugate. Another feature is from open loop complex poles, the root locus departs, making an angle with the horizontal line. So these are some of the features of root locus, and based on that, the Evans have proposed the procedure, the generalized procedure of plotting root locus. Now, this procedure is very important for the beginners, so try to understand each and every step so that this procedure is helpful for you for solving some of the examples. In this procedure, there are total 10 steps. See, the first step, first always identify the open loop poles, not the closed loop poles. The starting point of root locus, the root locus always begins from the open loop poles, and of course with the static parameter k is equals to 0. The ending point of root locus, the root locus terminates either at open loop zeros or they at infinity. The number of branches, third step of our procedure, the number of branches of root locus are, if number of poles are more than zeros, then number of branches are equals to number of poles. If number of zeros are greater than poles, but it is rarely possible because the system becomes non-causal, and therefore most of the time P are equals to P is more than Z, and therefore the number of branches are equals to number of poles. In case if number of zeros are more, then number of branches are equals to number of zeros. Fourth step is existence on real axis. The root locus remains on real axis and is confirmed if the sum of open loop poles and zeros to the right of the section is odd. Step number 5. The breakaway points. On the root locus between two open loop poles, the roots moves towards each other as the gain factor k is increased till they are coincident. At the coincident point, the value of static parameter k is maximum as far as the portion of root locus between the two open loop poles is concerned. Any further increase in value of k breaks the root locus in two parts. That is, the breakaway point can be determined by rewriting the characteristic equation and therefore solving the value of s from the equation given below. We have to take the first derivative of the characteristic equation, that is dk by ds is equals to 0, and after solving that, the root will give you, the significant root will give you the breakaway point. The angle of asymptotes. The generalized procedure for constructing the further progress of root locus, this angle is helpful. So for the higher values of k, the root locus branches are approximated by asymptotic lines making an angle with the real axis, and the angle of asymptote is given by 2k plus 1 into 180 degree upon p minus z, where this k varies from 0 and it is up to p minus z minus 1. Seventh step, intersection of asymptote and real axis. The asymptotes intersect at point x on the real axis is given by summation of poles minus summation of zeros upon p minus z. Step number 8, intersection point with respect to imaginary axis. The value of k. So this step is very important because this k value will decide the relative stability. At one stage, the locus intersect the imaginary axis, and beyond that system becomes unstable. So the value of k and the point at which the root locus branches crosses the imaginary axis is determined by applying Routh's criteria to the characteristic equation. The roots at the intersection points are imaginary. In very few examples, step number 9 and 10 are required, which are the angle of departure from the complex poles, which are given by this phi d, and it requires the sum of the angle subtended by remaining poles and the sum of angles subtended by the remaining zeros. So this information will give you phi d. Another angle of arrival at complex zeros is computed by this, which is phi a, which is angle of arrival, which is equals to 180 degree minus phi z minus phi b, and phi z and phi p are respectively the sum of all angles subtended by the remaining zeros and sum of all angles subtended by poles. So this is the 10-step procedure, 10-step procedure, which is very useful for constructing the root locus. So in the next presentation, we will understand some of the examples for the construction of root locus. Thank you.